Okay, welcome to Lesson 9 of Module 1, Scientific Notation. So all of our work on exponents is going to come into play now that we're talking about scientific notation, which is a way that scientists use to write numbers. We saw this in the Powers of 10 video, and now we're gonna do some work using scientific notation and doing operations like adding, subtracting, multiplying, dividing numbers in scientific notation. Okay, so let's look at what we're talking about here. So if I have a number, 2,356, in the last section we approximated those numbers like that by just taking the leading digit, right here, the 2, and multiplying it by a power of 10 to get a number close. So 2 times 10 to the third is an approximation of this number. But we saw that we'd get rounding error with that type of thing. And so in this lesson, we're going to use scientific notation to get the exact number and not just an approximation. Okay, so what am I talking about? Okay, so another example that I want to give you is stars in the universe. So there are a lot of stars out there, and an approximate number would be 6 times 10 to the 22nd. So that would be a 6 with 22 zeros. So it's a 23-digit number, 22 zeros. So what we could say is the order of magnitude of the number of stars in the universe is 22. Another way you may hear that said is the stars in the universe is on the order of 10 to the 22nd power. Okay, so that tells me ballpark what it is, order of magnitude. We talked about magnitude back in a previous lesson. Okay, so the magnitude of this number, which could be, I don't know, guests at some kind of sporting event or concert or something, is on the order of 10 to the third, or order of magnitude 3. So I know that it's in the thousands, right? Whereas this is in the whatever this is. I don't even know how to say that number, but I know that it has 22 zeros. So I know that if something has an order of magnitude of 23. It's definitely going to be bigger than any number. It doesn't matter what, I'm multiplying that by, it's going to be bigger. Okay, so order of magnitude is something to remember. And, this idea that we just use the leading digit here to do that approximation, okay, just to get an approximate number. Okay, so when we write numbers in scientific notation, we're going to follow a couple of guidelines. And so, let's just read it. A positive finite decimal, and a number S. So you have a number S, you want to write it in scientific notation. It's going to be a product. Okay, so notice this is a product right here because we're multiplying a number and a power of 10. So D is a finite decimal. In other words, it's not repeating, has a certain number of digits. And D is between 1 and 10. So it's greater than or equal to 1. It could be equal to 1, but it has to be less than 10. In other words, it has only one digit before the decimal place. Okay, so it's a number between 1 and 10, and N will be an integer. Okay, so we've got a number in scientific notation if it's a product of a decimal number, D, and a power of 10. And D has to be between 1 and 10. And if we write it that way, then N will be the order of magnitude. So let's look back at the numbers that we had in the previous example. Up here we had 2. 2 is a number between 1 and 10. And here's our power of 10 right here. So 2 times 10 to the third is in scientific notation, as is this. 6 is a number between 1 and 10, and then here's the power of 10, and it's a product. Okay, so both of these numbers are expressed in scientific notation. Okay, so I'm going to look, before we get into your exercises in the book, I want you to look at this next example. So here's a number. The number is 234 and 567 10,000ths. Okay, so 234.567. And there are 6 different products down here. So there's a number times a power of 10 in all of these cases. Now, all of these products are exactly equal to this value, to 234 and 567 10,000ths, okay? But only one of them is following the rules of scientific notation. So notice we want to be able to look at this exponent here, this n, and be able to say that it's the order of magnitude of the number. But look here, I've got 2, 0, 3, negative 3, 10 to the first power, there'd be a 1 right there, and negative 6. So what is the order of magnitude of this number? Well, the only way I can tell is if it's written in scientific notation. So I'd like you to look at these numbers and say which of these 6 follows the rules of scientific notation. Which of these 6 numbers? And so pause the video and think about that and be able to explain why it's in scientific notation. Okay, so if you said this first one, you're correct. The reason for that is that this is the only one where the number, the decimal number out front, is between 1 and 10, greater than 1 and less than 10. The decimal place is right after the leading digit, so it's 2.34567. And and if I multiply that by 10 squared, I would get, 10 squared is 100, I would get 234.567. Because every time I multiply by 10, I'm just moving the decimal place, 1 place to the right. Okay, so that number's in scientific notation, whereas this one is not, okay? This one is exactly equal to this, because 10 to the 0 is 1, right? So this is 234.567. This one right here, multiplied by 10 to the third, or 1,000, would get me back to the number up here. But this number is not between 1 and 10. Okay, so this is the only representation that allows me to look at the exponent and say the order of magnitude of this number right here is 2. And that's what I want to be able to do. That's the whole point for making this number be between 1 and 10, is that so that I can look at the order of magnitude, I can compare it to other numbers, I can talk about it, okay? The order of magnitude is not 3, it's 2, because this number is really, would be approximated by our old method of doing this by 200. This number's close to 200. It's on the order of 10 squared, or 100. Okay, so I hope that's clear. Let's look at our next example. Okay, so now you're going to look at exercises 1 through 6 and take a couple minutes to just work on these on your own. And you're just asked to answer the question, is the number written in scientific notation? And if not, give the reason why it is not in scientific notation. Okay, so go ahead and pause now and do that. Okay, you can quickly look over the results here, and I'll just quickly go down. Exercise 1 is written in scientific notation. This number is between 1 and 10. It's a product, and it has a power of 10 that it's being multiplied by. Exercise 2, this is not in scientific notation, although we could change it a little bit to make it in scientific notation, but the number, the decimal number out front, in this case, is less than 1, and it needs to be greater than or equal to 1. All right, exercise 3 is in scientific notation. 7.99 is between 1 and 10, and it's being multiplied by a power of 10. Okay, exercise 4, you may have been tricked, but notice it's not a product. They're adding these two numbers together, not multiplying them. And so this would not be in scientific notation. Neither would exercise 5, because for two reasons. First is the number D out front here, the decimal number, is greater than 10. It's not a number between 1 and 10. And I've got a power of 5, not a power of 10. So that fails on two accounts. Okay, and then the last one is written in scientific notation. The number out front is a number between 1 and 10, and it's being multiplied by a power of 10. All right, I'm going to do a couple examples that aren't in your notes, so you can follow along, take some notes if you'd like. And so this first one says to find the difference in population between Texas and North Dakota. And so Texas's population is given at 26 million. North Dakota is given at 69,000. So if we want to find the difference in population, we're talking about what operation? We're talking about subtraction, right? So if I want to find the difference between these two, I need to subtract. So this is an example where, it could be argued that I could there's not so many digits here that I could line them up and subtract, okay? But what I want to do is use this simpler example to show you how you could do this operation in scientific notation. And I think by doing it with numbers that are a little easier to grasp, that it will be a little more clear. Okay, so the first thing I'm going to need to do is to write the two numbers in scientific notation. So this one I'm going to have you think about it. How would you write these numbers in scientific notation? Remember, I need a number between 1 and 10, and I want to multiply it by a power of 10. And like we said in earlier examples of this, we rounded, and we don't want to do that. We don't want to round these off. We want to keep all of the digits of the number. Okay, so you could pause and think about how you would write that. What would the order of magnitude of both of these numbers be? So what would that exponent be on the power of 10? Okay, so take a stab at that, and then come back and we'll do it together. Okay, so Texas is 26 million. So what I want to do is I want to write the decimal part. If it's going to be a number between 1 and 10, I've got to put the decimal right after the leading digit. Okay, so the leading digit is 2. So the decimal is going to come right after that. All right, so now I've got 2.6. Well, what do I need to multiply 2.6 by to get 26 million? So what I'm looking at is decimal places. So if the decimal point was right here between the 2 and the 6, I'm going to count to where really I want the decimal over here, right? So it's 1, 2, 3, 4, 5, 6, 7. So this would be 2.6 times 10 to the 7th power. So the order of magnitude of the population of Texas is 7. Okay, this next number, North Dakota, I want to place the decimals right behind the leading digit. So I'm going to have 6.9 times, and then now I need the power of 10. 10 to what power? The way I'm going to figure it out is to count decimal places back to over here, where the decimal place is for this population number. So from here, between the 6 and the 9, I'm going to go 1, 2, 3, 4. So this is 6.9 times 10 to the 4th. So the order of magnitude of the population of North Dakota is 4. You know, it's in the 10,000s. This is in the 20 millions. And that's what this order of magnitude is telling us, is just how much bigger those numbers are. So now I need to subtract. Well, obviously, you saw how I had those numbers lined up before. We have to account for place value when we subtract. And so we have to have the same power of 10 on these numbers when we're subtracting them. Okay, so let's look at how this works out when we go to do the subtraction. So the subtraction that I want to do would look like this. It would be the 2.6 times 10 to the 7th minus 6.9 times 10 to the 4th. So here's a product here, here's a product here, and I'm subtracting them. All right, but I know that I have to deal with this place value issue. I can't just take 2.6 minus 6.9 and then figure out something with these exponents, okay? Because you saw when we lined these two numbers up how much bigger 26 million is than 69,000. So what I want to do is I want to work it so both of these numbers have 10 to the 4th here. So I've got 10 to the 4th on 69. So I need some number times 10 to the 4th minus 6.9 times 10 to the 4th. And so what's happened here is we've broken up 10 to the 7th into two parts. We're now thinking of it as 10 to the 3rd times 10 to the 4th. And think about your exponent rules as to why I can do that. All right? Okay, so let's see if you can figure out the reason why I'm doing this. All right, so now I have 2,600, and that came from here. 2.6 times 10 to the 3rd is 2,600, and that's times 10 to the 4th minus 6.9 times 10 to the 4th. Now, why did I want my powers of 10 to be the same? Well, it's because I want to use the distributive property, and I want to pull out the 2,600 minus 6.9 times 10 to the 4th. So I pulled the 10 to the 4th out of each of these using the distributive property. Now I can subtract, and I get 2,593 and 1/10 times 10 to the 4th. Okay, so I've kept my place values in the right place. And when I write that as a number in standard notation, I need to take this decimal point and move it 1, 2, 3, 4. So I need to add some zeros to that. So here's where it was over there between the 3 and the 1. 1, 2, 3, 4. And it ends up right here after that 0. So the difference in population between Texas and North Dakota is 25,931,000. All right, and this number could be written in scientific notation, and if I did, it would be, here, let's put it up higher. It would be 2.5931 times 10 to the 7th. Okay, one more example before we get to your exercises in the book, and this one has to do with very small numbers. So if you know anything about atoms, you know that they have mass, but they have very small mass. So here's a water molecule. It's composed of an oxygen atom and 2 hydrogen atoms bonded together, H2O. All right, and so we're going to find the combined mass of all the atoms in a single water molecule. All right, so we're given the mass of a hydrogen atom, and it's this number. Notice the decimal point here, and then a whole bunch of zeros, and then some digits down here, and then an oxygen atom. So it'd be useful to know the order of magnitude of these two numbers. Okay, so the oxygen atom is actually a bigger number. How could we know that the oxygen's atom's mass is larger than the hydrogen atom? All right, well, if we write these two numbers in scientific notation, we will be able to look at the order of magnitude because it will be the power of 10 that goes along with it. So let's look first at the hydrogen atom. So we want to come up with a number. We want to use the digits in these two numbers here and write it in scientific notation. So a number between 1 and 10 would be 1.7. So I've put the decimal place here. In order to, I need to multiply by a power of 10 that's going to move me this many decimal places to the left. And so if I count those, I count from the 1 all the way over here, I count 27. So this is going to be times 10 to the minus 27. 1.7 times 10 to the minus 27 kilograms, because there are 26 zeros plus one more place. All right, and then for the oxygen atom, I've got 2.7, giving me that number between 1 and 10. I'm going to put my decimal place right here, right after the leading digit, 2. 2.7. This time, though, to get here, there are only 25 zeros plus one more place, the 2. So this is times 10 to the negative 26 kilograms. So you can see by counting those zeros that the oxygen is 1 order of magnitude greater than the hydrogen. It's 10 to the negative 26, and this was 10 to the negative 27. Okay. But we've been asked to find the total mass of a water molecule. So we need 2 of these and 1 of these. So 2 times 1.7 times 10 to the negative 27 is equal to, so I'm going to multiply those together. This is really 2 times 1.7 times 10 to the negative 27. So I can think of this, well, I can write this as 3.4 times 10 to the negative 27. So I just doubled the hydrogen's mass to get that. Now I want to do 3.4 times 10 to the negative 27 plus 2.7 times 10 to the negative 26. So once again, because I'm adding these two, I need to make sure that the place value on the decimal numbers, when I will go to do the math there, is adjusted so that these exponents have to be the same. Because they're not, I have to do some adjusting. All right. If I went back and looked at those numbers, I would see that I need to line them up to be able to add them. I need to line up that decimal point. Okay, so the way I'm going to do that is by splitting this 10 to the negative 27 into 2 parts. 10 to the negative 1 times 10 to the negative 26. So because negative 1 plus negative 26 is equal to negative 27, I've just adjusted that number. So I've got 3.4 times that, power of 10, again, plus 2.7 times 10 to the negative 26. Okay, so 3.4 times 10 to the negative 1, I want to combine that, so I'm going to do that. And so when I put those together, I'm going to get 0.34 instead of, so I've taken the 10 to the negative 1 and moved the decimal place on this one place to the left. Okay, so this is times 10 to the negative 26 plus 2.7 times 10 to the negative 26. Now I can use the distributive property. Whoops, I see something I did wrong. This should be a 26 here now, right? Because we fixed that. Okay, so now I've got 10 to the 26, 10 to the negative 26 here and here. So I can add, I can pull that out. So I've got 34 hundredths plus 2 7/10 times that factor of 10 to the negative 26. And this equals 3.04, 3 400ths times 10 to the negative 26. So that's my combined mass right there, 3.04 times 10 to the negative 26. Okay, so these are some complicated examples. We're going to do a few exercises now that are a little simpler. The reason they'll be simpler is because the powers of 10 on the first few problems we do will already be the same. Okay? Okay, so for the next few lessons, we're going to be doing operations with numbers and scientific notation. All of these problems will have a context. In other words, you're going to read about something. You have to figure out what to do with the numbers. So the fact that they're in scientific notation is one thing, but just knowing what to do with the numbers is another, okay? So especially if you haven't had a lot of experience with quote-unquote word problems. Okay, so you could be asked, how much larger is one thing than another? How many times larger is one thing than another? What is the difference between blank and blank? What is the ratio of blah, blah, blah? And what is the average? Okay, so think about what, as you read these problems, think about what operations you would do. So right now I want you to think about what operations you would do for these 5 different problems. What would you do? Okay, so for these first 2, how much larger is something and how many times larger is that? If I just need to know how much larger, that's a subtraction problem. Okay, I just subtract the smaller one from the larger one, and then that gives me the how much larger something is. But how many times larger it is, say, you know, somebody is 6 feet tall and another person's only 3 feet tall, that taller person is 2 times larger than the first person. So this is actually a division problem. So it's just one word that makes the difference. How, you know, instead of how much larger, how many times larger. Okay, so to find out how many times larger something is, I have to divide to know that. What is the difference between those 2 things? Well, that's also subtraction. Difference is subtraction. What is the ratio? Here I'm going to set up a fraction. You know, I'm going to set up a ratio of A to B, and maybe I'm going to simplify that ratio. Okay, so that's kind of division there. What is the average of a bunch of numbers? Well, here, remember how to do average. I'm going to add, then divide. Okay, so that's just a quick review, but I just want to encourage you to read each of these problems carefully. Some of them can be a little tricky just to know how to proceed. Okay, so now what I want you to do is look at exercises 7 through 9 and do your best to work through those and then come back and check them against the video. Okay, now we're going to go through these exercises and look them over. If you want to just do this with the teacher's notes, that's fine too. But I'll go through just some explanation of how we can use the scientific notation here. So for this first one, exercise 7, we wanted the sum of the debts of the 3 most populous states. So that would be California, New York, and Texas. And these are the debts written in scientific notation. They all have the same order of magnitude, notice, and you can see that from the table by looking at their place value. They all line up right here, have the same exact number of digits. So I'm just placing the decimal point after the leading digit to write all 3 of these numbers in scientific notation. So once we've done that, then we can notice that they all have the same power of 10 because they're the same order of magnitude, and I can factor out that power of 10. So I've got the decimal parts, which I can now just add together, and all those will be multiplied by 10 to the 11th. That gives me 10.2 times 10 to the 11th. Now the directions specifically say to express in scientific notation. The answer that I've come up with here is not in scientific notation. It has a decimal part and a power of 10, and it's a product, but this number is not less than 10. So I just have to adjust the power of 10. So here's how I do that. I think of 10.2 here as 1.02 times 10 to the first power. So if I see this 1.02 multiplied by 10, then I'm going to get this. And I still have that multiplied by 10 to the 11th. And now I'm going to use the associative property, and I'm going to combine 10 to the first and 10 to the 11th. And when I do that, I get 1.02 times 10 to the 12th. So these two numbers, again, same exact value. This one is not in scientific notation. This one is. Okay, let's look at the next one. This one, I want the sum of the debts for the 3 least populous states. So that's, going back to the table, that's 4 times 10 to the 9th, which is, let's look at it, is that 4 billion, right? 4 billion. So 4 times 10 to the 9th plus 4 times 10 to the 9th plus 2 times 10 to the 9th. And I can again factor out that 10 to the 9th and put into the parentheses the 4 plus 4 plus 2, which adds up to 10 times 10 to the 9th. The 10 can be rewritten as 1 times 10 to the first. The reason I'm doing that is because, once again, this number here, 10 times 10 to the 9th, is not in scientific notation because this part needs to be less than 10 and greater than 1. So that's why I'm doing this. And then finally I can write it as 1 times 10 to the 10th, and that is in scientific notation. Okay, this next problem asks, how much larger is the combined debt of the 3 most populous states than that of the 3 least populous states? So remember, we said how much larger. That's going to be a subtraction problem. How much larger? I just subtract the smaller from the larger, and I get the difference. All right, so I've got 1.02 times 10 to the 12th minus 1 times 10 to the 10th, and those are the results from the first part A and part B. Okay, so I'm subtracting, but notice that my powers of 10 are not equal, so I can't factor them out until I do some adjusting. So I'm going to adjust this first one. I'm going to break 10 to the 12th apart into 10 squared and 10 to the 10th. And then I still am subtracting, I went a little bit more than I wanted to there. I'm still subtracting 1 times 10 to the 10th, so that didn't change. Now look at this part. So what I'm going to do is I'm going to combine the 1.02 times 10 squared. This is going to move the decimal place 2 places to the right. So now I've got 102 times 10 to the 10th minus 1 times 10 to the 10th. And again, now I can factor out this 10 to the 10th because they're the same. When I do that, and then I've got the 102 minus 1 in parentheses times 10 to the 10th. So that gives me 101 times 10 to the 10th. Once again, not in scientific notation, but I can do some adjusting. So I have rewritten 101 as 1.01 times 10 squared. And I still have this times 10 to the 10th. And so I can write that as 1.01 times 10 to the 12th. Okay, when you get good at doing this adjusting, when you have scientific notation like this and you need to adjust it, you may be able to go right from this step to this step, but I notice that a lot of people make mistakes. Like they might think this was an 8 by subtracting 2 instead of adding 2. So it's important that you get that right. And so I think taking that little bit of extra time to realize how we can break these numbers apart is helpful. All right, so this next problem says, what is the sum of the population now of the 3 most populous states? So now we're looking in that last column. And these are all order of magnitude 7, which is nice because now I know I can just add the decimal parts here by factoring out the 10 to the 7th. So that would look like that. So I've got 3.8 plus 1.9 plus 2.6 times 10 to the 7th because I was able to factor out that 10 to the 7th. If you're going to use a calculator on these, it would be for this part, right? It would not be putting the entire number into your calculator, but if you want to put in 3.8, 1.9, and 2.6 to get 8.3, that's perfectly fine. But just let's not use the exponent feature just yet. Okay, so 8.3 times 10 to the 7th, and I look at that number and I realize it's in scientific notation, so I'm done. Because 8.3 is between 1 and 10, just has that one leading digit. Okay, sorry about that. So let's look at part B, the sum of the population of the 3 least populous states. So those are all order of magnitude 5. They're 6-digit numbers, and I can write them in scientific notation like this. Since they all have that factor of 10 to the 5th, I can factor it out using the distributive property. Add the decimal parts, and again, if you want to use a calculator on these, that's the place to do it. So now I've got 18.92 times 10 to the 5th. I'm going to adjust that by realizing that 18.92 is 1.892 times 10, and that all times 10 to the 5th. And then combining those powers of 10, I get 1.892 times 10 to the 6th in scientific notation. Okay, so now I'm being asked something else in part C. I'm being asked how many times greater is the total population of California, New York, and Texas compared to the total population of North Dakota, Vermont, and Wyoming. So remember, how much greater would be a subtraction problem. How many times greater is a division problem. So I would set it up like this. I want to know how many times greater this number, the 8.3 times 10 to the 7th, is than this number. And this fraction here is going to give me that answer. Now I know this is bigger, right? Because 10 to the 7th is a whole order of magnitude bigger than 10 to the 6th. All right, and so I've got that division problem. When I have those powers of 10, remember we can break it up into 2 fractions. We can do the decimal part, and then we can simplify the power of 10 part. So when we do that, another good use for calculators right here. 8.3 divided by 1.892 is approximately 4.39. 10 to the 7th divided by 10 to the 6th is 10 to the 1st. Okay, 7 minus 6 is 1. So this is just times 10. I'm not going to leave my answer here in scientific notation, although it is, because I'm being asked how many times greater. So if I just multiply that out by 10, I've got 43.9 times bigger or greater is the population of those more populous states. So I could even round that to 44 times greater, approximately 44 times greater population in those more populous states. All right, exercise 9 asks you to find the average distance of the planet Uranus from the sun. And so to find the average, I'm going to take the furthest distance, add it to the closest distance, and divide by 2. I'm finding, a number in between those two numbers. So these have the same order of magnitude. They're both 10 to the 9th. So I can just add 3.004 and 2.749 and get 5.753 times 10 to the 9th divided by 2. So then I'm going to take and do that division first, divide up, the numeric, that decimal part, and then the power of 10. So I get 2.8765 times 10 to the 9th, and those distances were in kilometers. So that would be the average distance from the sun. Okay, let's do a quick review. So here's the definition again of scientific notation. We've got this decimal, it's a product of a decimal number and a power of 10, where the number is between 1 and 10. The decimal number is between 1 and 10. And if we write a number that way, then we can use the exponent to immediately see what the order of magnitude of this number is. Okay? So here's an example of two numbers. So I've got 6.2 times 10 to the 25th and 652.78 times 10 to the 25th. What is the order of magnitude of those two numbers? So I can tell right off for this number here that the order of magnitude is 25 because I have 6.2 written in scientific notation, or between 1 and 10. So that number is in scientific notation, whereas this other number is not. I've got 652 times 10 to the 25th. So the order of magnitude is not 25, but if I rewrite this in scientific notation, this would be times 10 squared times 10 to the 25th. Okay, so if I go two places there, that gets me back to my 652. So this is 6.5278 times 10 to the 27th. And the order of magnitude on that number is 27, not 25, even though the power of 10 shows 25. This number here has to be between 1 and 10. You just want one leading digit, like this, one leading digit, and then the rest after the decimal point. And that will give us our order of magnitude. Okay, and that will help us to compare these numbers at a glance. All right, so good luck with the exit ticket and the problem set. Remember to always think about what is the problem asking you to do with the numbers. Add, subtract, multiply, or divide.